Good day, everybody. This presentation is on liquid air energy storage, or LAES. It'll be used like that in the presentation, so do keep that in mind. And it is by myself, William Parent, as well as Jacob Finch, Jeremy Harvey-Rosa, Kijil Liang, Maxim Sarmatsev, and Sarah Tavasoli.
Before we talk into details about liquid air energy storage, I wanted to talk about why in modern time, there is a need for renewable energy storage technology. Firstly, well, it has the tremendous capability of helping in reducing greenhouse gas emissions on a global scale in a more affordable and efficient way. So not only can it help us decarbonize our energy sector over time, but it can also help prevent global warming from surpassing the current Earth temperature of 2 degrees Celsius above zero, just like any most renewable energy systems. But what makes energy storage technology even more special is that, unlike wind turbines and solar panels, which heavily rely and are limited to their geolocation as well as the amount of wind and sunlight they're getting, energy storage technology can be practically used everywhere at any given time. This not only makes energy more accessible to everyone, but it can also be work hand in hand with these two previous renewable energy systems that I had mentioned, by making up for what they lack for, which is constant production of energy and electricity. Because as I mentioned, these heavily rely on the amount of source that they get, the energy source that they get. So their weather is unpredictable, and you can't necessarily always get the same amount of sunlight or wind, and therefore it affects your electricity production. But energy storage can make up for these more less productive times. Um, Thirdly, energy storage technology has a low investment cost, which means that many countries who have difficulties transitioning from fossil fuel energy systems to renewable ones, they'll have a more affordable option instead of solar or wind, for example, and they could also be able to provide electricity for various communities that still lack electricity to this day. And finally, energy storage technology is generally less expensive to operate. Damage control is also less expensive in contrast to fossil fuel or any other types of renewable energy systems. And it's also more economically beneficial on the long run, because as the world is sort of shifting from fossil fuels to renewable energy, it will be expensive to replace everything fossil fuel related, because we've been so accustomed to it and used to it for a long time. So it will be expensive to replace it, but on the long run, it will actually be more profitable and more economically beneficial, as I had said, for governments, companies, and so on.
So let's talk about the basic operation of liquid air energy storage. So we're going to start by talking about the main components. So we have air liquefiers that use excess electricity to produce liquid air. We have the cryogenic tanks that are used to store the liquid air. And we also have the power recovery unit, where the gasified liquid air is used to drive a turbine which will generate electricity. We also have heat storage and cold storage units that will capture and store cold and heat waste from the process. So the operation is separated into three distinct phases. The first one being the charging phase, which consists of air liquefaction. The second one being storage, which involves the preservation of air in liquid form. And the third one being the discharging phase, which consists of recovering the energy through pumping, reheating, and expanding the liquid air. So here's how it works. During the charging process, the excess electricity during off-peak times is used to clean and dry the air coming in the air liquefier. The air is then liquefied through a series of compressions and is refrigerated. After that, the liquefied air is stored in the cryogenic tanks where the temperature is around 196 degrees Celsius below zero at an atmospheric pressure. The discharging process starts when energy needs to be recovered. The liquid air is pumped at high pressure and evaporated. It is then expanded by using heat and it will result in high pressure gas, which is then used to drive the expansion turbine generator, which will generate electricity. In addition, the cold thermal energy from the evaporation stage is captured by the cold storage units, and the energy will be recycled by using it in the refrigeration stage. The same goes with the heat waste produced in the compression stage. It will be captured by the heat storage units and will be used to reheat and expand the air. Both thermal recoveries will enhance the efficiency of the process.
Let's talk about the principles of physics behind liquid air energy storage. So basically, liquid air energy storage relies on air compression and expansion in order to be able to store excess energy and export it back to the grid. These transfers of energy can be seen with the compression and the expansion of the air, which is coherent with the definition of work, which is the transfer of energy from one place to another. In this case, work can be represented by the integral of P times dV from VO to VI, where P is the pressure, dV is the volume change, and VO is the initial volume, and VI is the final volume of the gas. For the discharging phase of the system, as air expands, positive work is done on the system by the gas, making the system receive a form of energy to export it back to the grid by converting it to electricity. For the charging phase of the system, as air compresses, negative work is done on the system by the gas, thus absorbing the energy for storage. Round-trip efficiency is a way to measure the efficiency of energy storage systems. It is basically the percentage of electricity put into storage that can be retrieved later. The higher the percentage is, the less amount of energy is lost in the system. The formula for the round-trip efficiency is the Greek symbol eta equals Y times Wt divided by Wc. Wt represents the specific power output during discharge. Since power represents work divided by time, this is basically the rate of work done by the gas during expansion, which in final is the rate of energy released into the grid. Wc represents the specific work rate for air compression during the charging phase, which is basically the work done on the system during the compression of the gas. And finally, Y, being the liquid yield, is the ratio of the rate of the liquefied airflow to the rate of the total airflow.
So what does it look like in real life? The efficiency of a hypothetical liquid air energy storage facility would reach around 50 to 70%. Currently, the technology tells us that the normal round trip efficiency should be around 50%. However, in the future, with the development of better equipment, we could reach around 70%. About cold energy recycling, again, in the future, we could reach around 70% of cold energy recycling, meaning that around 70% of the cold energy that we use to refrigerate the air could be used again to refrigerate more air. And moreover, we can share cold energy with refrigerated warehouses near the facility if the location allows it, which again helps with the round trip efficiency if we calculate that into it. Capacity, size, and power. A pilot plant that was installed in England a few years ago achieved a power rating of around 350 kilowatts per kilowatts. However, a theoretical plant of higher capacity could reach around 10 megawatts. The rated storage capacity of this pilot plant was around 12 2.5, sorry, megawatt per hour, but a theoretical higher capacity storage capacity could reach around 100 megawatts per hour. And finally, although we don't have the metrics for higher capacity storage, we can deduce that would be of magnitudes larger than the pilot plant, which was with a capacity of a 60-ton tank for the liquid air.
So, for the pros and cons of liquid air energy storage, it's going to sound quite amazing. It's going to sound like I'm trying to market it to you guys. I'm not. It's just generally very good. There's one big pro, two smaller pros, one big con, and one thing I marked as indecisive. Because as of right now, it is a con, but with time, it'll gradually become a pro. So, but I had to mark it there because it can be viewed as either. So, yeah, it's important. The two smaller pros are that there are no geographical constraints. This means you can build it anywhere on any surface. You know, it doesn't have to be like hard ground or anything because all the compartments can float and have their own foundations. Then there's also an option for hybridization. That means that you can combine it with other forms of energy storage, like compressed air or like even lithium ion at certain places. And this makes it so that the con, which I will discuss later, is slightly reduced. The big pro is the option for compartmentalization. I was kind of specifying that a little bit with the hybridization. You can add little compartments between each of these three main compartments that the system uses, and that's the charging, storing, and discharging parts. All of these are individual compartments and can be sized and worked with individually, which means if you want to charge really, really quickly, you can have a big charging compartment and a very small storing compartment, or you could have a big storing and small charging or discharging. The big con is the energy loss. This to describe this, they use something called the RTE, or round trip efficiency, and this is a percentage of how much energy you will get depending on how fast you charge or discharge or how you manage the system. This is the biggest con because between each stage, the charging, storing, and discharging stage, there is energy lost as depicted by these little arrows here. And the best we've ever seen for energy conservation was like 70%, and that's really, really bad for energy storage mechanisms. Most are significantly better than that. Then the indecisive is the cost, because right now it is extremely costly to start with the system. There's very little research and work that has been done. There's only one plant, or maybe two plants, I think, that are active right now on the planet on a big scale. So right now it'll be very expensive, but with time, because the material and management costs are not very expensive, it'll slowly but surely become cheaper.
Okay, so now we're going to talk about the viability of this technology in the future to solve the energy crisis. But before looking at this, I think it's important to look at the situation right now. So, currently, there are not many liquid air energy storage facilities being used. This is the first one ever built that was an actual attempt at storing large amounts of energy with liquid air. It was built in England in 2018, which means the technology is very new. It's been known before and it's been tried before, but this is the first one at a large scale. Right now, pumped hydroelectricity storage is by far the most common, but it does have that natural barrier that you need water, and it's currently very expensive for liquid air energy storage. So, in the long term, is it a viable technology? Well, as discussed in the pros and cons, there are many advantages to this technology, like the lifespan is much longer than most battery technologies. As you can see in the graph on the right, the power rating and the rated energy capacity are both very good, as the liquid air energy circles are in the top right. It's likely a solution to the environmental dependence of the hydro. As I previously said, you need water. There are also many possibilities for technological advancement, since the technology is very new for 2018. So, is it viable in the future? Well, I think so, but I think you need to make it at a very large scale so that it reduces the price, because right now it's really expensive. So that's it. These are the references.